Yes, good morning, colleagues in the industry. This is Michael. Just to start our day, first apology. I think for a week ago I posted some knowledge sharing on post-tensioning box culvert, but later on I saw comments that the sound wasn't there, so I removed. Since then I've been trying to sort out. At least yesterday one of my young engineers helped and sorted out this thing. So I said let me replay this topic that I had shared with you and withdrawn. Let me share again because that is something that I thought I should share. Okay, so this is yes, design of prestress concrete box girder using Midas Civil. Definitely we have talked a lot about Midas Civil. That's my choice. From 2018 when I learned Midas Civil, it has been a very good software. I feel comfortable using, and I'm still learning more. I will get more time and also learn. It's a good software comparable to others. I know we have the CSI, we have the lib, losers and the rest, but I found this a bit user-friendly. So this brief or knowledge sharing is being done by Michael Chola, a registered engineer with ERB Uganda. I'm a UIP member, Uganda Institution of Professional Engineers, Uganda. I'm also a member of PIAC, International Road Association, Bridge Technical Committee, 24-27. We are getting a lot of experience from very experienced and well exposed world professionals. That is something that I got to learn from the time I joined last year. I've been following. I think PIAC is doing very well. Four things that I've picked and I'm trying to get deeper into. One is the issue of diversity in design. We need to begin involving institutions, various institutions and bodies and communities into our design so that we have a better design that is fit for purpose. The issue of redundancy also is something that we need to take care of. Most of our structures we have been designing since in the 60s, early 60s and 50s and 30s, they were more on economy. We look at, I have this money, so you work backward. But now when time comes for retrofitting, you find that the risks of retrofitting become a bit high because you don't have redundant member to help to transfer loads in the event that one key element is supposed to be retrofitted. So right now we are getting back into conservative design or having design catering for one or two or more extra load paths that in the event of repair or strengthening you are able to retrofit without worry. The issue of climate change adaptability also need to be taken care of. So you find over time, because of land use, because of change in the climate environment, most of our designs have a bit of laxity in terms of consideration of openings to take care of, especially in floods and flooded areas, mountainous areas with unused terrain, low-lying areas. So we really need to be mindful of that. I think There's also issue to do with forensic engineering, where if a bridge collapses or a building, you have to do assessment to discover or to find out the cause. So the issue of monitoring and inspecting post-tension or pre-stressed concrete girders or post-tension box girders is also an element that the PIAC community tends to talk about, and so many things. The issue of practices, the issue of compliance, the issue of improving on codes of practice and the rest of it. So there are quite a number. I think we shall continue to learn on that. So a project management professional from PMI USA. Definitely, we talk about Midas, but that's an element in the bigger dimension when it comes to project management. Because Midas is done by work done by a CAD engineer. But a CAD engineer, when you look at the structure organogram in the building industry, is could be is a design engineer. But you also have other professionals and key personnel. So it's one of the key elements that which form part of that. So project management become bigger than the use of Midas. So in the title slide we have design of pre-stressed concrete box girder using Midas. Then we have in the subtitle we have overview of the design process, and then the piece was prepared by Michael and the date was started. Remember now, I think from that, I think that's I tried to modify this after I withdrew the other one when it failed to work. So in the introduction, pre-stressed concrete box girders are structural elements used in the bridge construction, characterized by their hollow cross sections and pre-tension stroke post-tensioning tendons. Advantages of using box girder is a high torsional stiffness. It also has a reduced self-weight. It has aesthetic appeal. It looks good, and then also improved durability. But of course, the improved durability also depends on how best you look after your structure. It doesn't do work on its own, but how do you follow it up? Common applications of box girders are basically highway bridges, railway bridges, viaducts. Yeah, those are the common areas they apply that. Design consideration, we look at the span length. You have to look at the cross sections. You have to look at the materials. Basically, for this long span and pre-tension or post-tension structure, they use high-strength concrete and pre-stressing strands. Pre-stressing strands are steel with very high tensile forces, which is almost 3 times the normal steel we use for building construction or for reinforced concrete. Loading conditions are always also taken care of. I think here we are done. I think here I picked IRC, but of course we have BS, we have Eurocodes, we have Ashito, so quite a number. Modeling in Midas Civil, what do you do? Here now, this is where you do the definition of sections. You also can define your materials. You input all your geometric properties and materials, and normally you actually look here. You create your node system. You create where the locations. You come to properties. Property of materials are all here. You look at the time-dependent materials. You have different. This is like concrete. So this is where you create your materials to be used, boundary conditions and other things. So basically that is now when you are in Midas Civil. Structural model creation using you can use this if you are dealing with balance cantilever. There are also other wizards, like if you are dealing with your post-tensioning. These are pre-stressed concrete composite bridge, also post-tensioning. You can do the wizard. or basically this is where you have the wizard, but you can, for this box girder, it is normally rare. You can actually use, basically these are the precast eye girders. Yeah, so this is then construction stage. You have to know the definition of construction staging. Definitely construction stage sequence is very, very important. If I could quickly take you somewhere here, you see construction staging is when you come for loading, construction is here, construction stages are here. So for construction staging, you see this is where you define your structural group system. Now, like for this one, my stage 1, of course, the first stage would be to construct the substructure system. What do we mean by substructure system? I have abutment which are represented by a boundary condition this side and also here. Then this is the pier support minus the pile cap and the pile. So the substructure system would be the abutment and the pier support, while the foundation would be the pile cap coming down. But sometimes we put them all together. So this is what you would call construction stage. For construction stage 1, this is your support system. You can see here representing the abutment, and this is the pier. Then construction stage 2, you see now what it is. Now, then the third stage is so all these stages must be modeled and catered for. Excuse me. Taken care of, and taken care of in your analysis and everything. So this is where I talk about construction staging. So then we can go to analysis and design. This is you do load applications, you do finite element analysis. Basically, Midas uses that, where now you do, for applying for the application, you do dead load, superimposed dead load. Dead load, this is now both superimposed dead load and the dead load from cell weight. Then live loads now can include even traffic, pedestrian, quite a number. Then pre-stressing forces, because for post-tensioning and pre-stressing system, pre-stressing forces you must also apply when you do the cable. It has to be, because you have to pull it and then allow it to exert force onto the member to be in compression. Then design checks you always have to do. Once you do your design, also it's important to do checks for compliance with codes and standards. So the good thing with this software, sometimes after doing the design, they will always give you a comparison with the allowable limits. If it has exceeded, it will tell you this is beyond, so you have to adjust the design. Then the results and optimization, comparing cross-section for economic design. This is the normal thing we normally do within the acceptable limits, determining the amount of pre-stressing steel needed. All that is just a matter of now. Maybe you find you have done more, would be about 80%, and 75 or even 60% can do the work. So you try to do an economy and even resizing the members, and then until you get what works, what's it fit for purpose. But again, if you look at the redundancy I talked about, therefore it might also be tricky if a 250mm section can work. And I don't think it has any impact if I do a 275 or even a 300. The impact will be minimal, because now that means the cover will be increased a bit, and then the carbonation ingress can be delayed further, and the section become durable to impair the integrity of the bridge. So that is a brief narrative. So the bigger question now is, what should a modeler be aware of? They said, okay, I'm going to model this bridge, I want to use Midas, I want to model it. So what are the requirements? First, you need to know the structure you're going to model. You need to be well versed with the geometry. You need to know the different elements, dimensions, all that you need to know. So you can see from this, I have abutment, This is the deck system over the abutment. So if you are to model, you need to see how these systems have been stuck together to work as one. This is the mid-span deck, just suspending in the air between the two support systems, and then this is the one over pier. So this is the pier support system. You can see the section over support seem to be as the solid. The gap is smaller than when it is in the middle. The question is why. You need to think about shear stresses and how to manage. So modeling requirement, you need to have knowledge in geometry and dimensions of the element you're going to work on, be it a girder, the entire structure. You need to know pier support detail. You need to have knowledge of tendon properties and layout you need to be aware of. Various loading categories also you need to be aware of. You need to know the different loads we have seen up, the dead load, the superimposed dead load, live load, temperature, earthquake, so many things. Section neutral axis. You should be aware that this is one of the guiding principles when you are trying to locate and lay your tendons. They are normally at the end support. It's very rare to see most of these anchored block above the neutral axis. It's always starting just within the neutral axis downward towards the middle of the span. You need to be aware of the structure and boundary groups, because these are the things that will help you to group your structures to do the construction stage sequencing. Construction stage requirement is also important, so you have to always, I've told you have to always come here and have a look at what do. You see the element, the boundary group, then the loading group. So you need to be aware of all this, and they are all created here, and that will also simulate exactly how you are going to construct this bridge. Where do you start from? That's exactly where you do it, and you give you the adequate time, load it, put all these other requirements, put the boundary conditions, and proceed. So that is why it is very important. The issue of transverse tendons, some like this box girder, sometimes you realize that even after pre-stressing and tensioning in the length of the bridge or direction of the bridge, transversely you may find that the overhang is too much, and then you find that when you check the local effect analysis and your design, you realize the cracks are still too much. So sometimes even deflection. So sometimes you have to apply transverse tendons, and then if you check most literature, do give some guidance on how to do that, but you can actually model it properly and then check, and you ensure that there's no stresses induced beyond limit. So that will be from first principle. Then the issue of number of cells. This one is single cells. There are text literature that guides on the thicknesses here, top flange, bottom flange, the web, then the overhang, the openings. Well, why would it be single cell, not double cell? So there are other philosophers who have already come up with after doing those research and those researches and the rest of it, they discovered that actually there could be some benefit in deciding on scientifically the use of single cell and the double cells. So that also you need to be aware as a designer, and then the one who's going to model, because now here you're not just on the modeling, you are now also a designer. So you have to read a bit widely and get more information to guide. And then the use of span depth ratio. Normally for all these span, whether it is 30 meter, 40 meter, we get guidance from most of these literatures we read. Most of the literature we read, so you get guidance on the span depth ratio. They tell you for pre-stressing system, for box girder, for PC girders, continuous or simply supported. balance cantilever, definitely you'll get guidance on span depression from the literature we have. Some manuals do have. You make sure make good use of that. And then the issue of bridge element loads to add. Like for this, if you look at this box girder, we have crash barriers. That's already an element. That's a bridge element. This one generates superimposed dead load because these are dead loads that they come after you have done all the construction stages. So you need to know the load or weight of this. Then the raised walkways, you need to determine the weight. Then the wearing surfaces or wearing surface here, you need to know the weight. Then if there are services, now all those different loading patterns need to be taken care of, and all that you group it under superimposed dead load. You could apply them differently, but when you get into the grouping, then you need to know where you take that. The survey data and levels and sections, because you need to know the levels, you need to know the terrain behavior, topology, so that you are able to model your substructure system. And then also even the top of the deck should depict exactly how if the bridge is on grade or on slope, you have to design it that way. If it is curved and also on slope, still you have to model that. So that knowledge is very important. This now takes you to role play. Who do you work with to make sure you have all the required information to help you do the modeling and the design? Then the issue of approach road designs, the highway person must come in. Then you get to know the profile, the way it is, so that you're also able to adequately model and design the fill, the retained fill behind the abutments. The use of hydraulics details, hydraulic details, the issue of openings, the headroom, the score depth, all those information. You need to know all the information which will guide your model. The use of the geotechnical data, the borehole data. Now, if you're going to model the issue of soil structure interaction, these piles must be modeled. So, what guides modeling is actually the issue of the geotechnical data or borehole data. That is very, very, very important. Short of that, you will not start guessing. So these are some of the things you need to be aware of. Normally a good modeler is the one that who understands the geometry, who can easily draft. Drafting, sometimes we say drafting is for technician, but even a designer, the engineer need to know, because that is where you understand the different elements of the structure. And when you are modeling, you know how to stack them to give you the real stuff that you want to model and analyze. So you have a span of 30. Now I think this moved. This span is this has to be in line here. Even this has to move. This unmoved should be slightly here. Or because if you adjust this, then okay, I see now why it moved a bit. So here, if you move like this, okay. So adjusting this member affects this span dimension. So basically, this span is given. The hydrologic guys always give you the internal dimension, and but for you now, based on this center line is now the engineer. So tendon layout profile guided by knowledge of slope at anchor block, and manuals and code requirements are here. So you can now see these are the different profiles that you need to be aware of. Even you need to sketch and see the different curve area, the minimum radius you're going to use. At this point, you need to know the slopes of at the anchor block. I think from using rule of thumb, it is 6 to 12% degrees. So this is something that you need to be aware of. It helps a lot. So without having some knowledge, because now even the different types of layout, you have the parabolic, you have the drape type. This seems to be like a drape type, but in the model you see like a bit curved. You combine the drape and so it's a hybrid type kind of modeling. Okay, so this is a typical section. You can see this is a mid span and this is an over support. You can see neutral axis, but this is the mid span. This is one way of defining your layout. Another one could be down here. So depend on how. Next time I will share the one which does it down here. So at the bottom flange. So this is running along the webs. So you see these are the depending on the number of the number and the area of cables here. You can do quite a number if you want. Here is only one column. 1, 2, 3, 4, and this 5. You can actually do two columns per web if you want, depending on the loads and the span. Okay, so basically various sources of data for modeling the box girder. This is girder end anchor block detail. This is very important actually for post tensioning or pre-stressed concrete. If your anchorage or anchor block details are not well done, if there are defects, definitely that girder will not work very well, because all the tensioning and holding of the tension is done, or they are done at the end section of the girders. So this is where the wedging is done, the jacking is done, and so even the jacking force is applied here. These are the plates. You must also be designed, and then the manufacturer can, once you have all the forces, manufacturer is able now to give you the detail to use for this one. We're going to see it down here. I also try to bring this out for those young people who would wish to go and read, or who are going to do the further studies in post tensioning. There is this diagram they talked about, Magnell diagram. When there's a book called Pre-Stressed Concrete Design by M.K. Ast. When you read that, you will find it has it's always used to guide you on optimizing your eccentricity and also pre-stress forces. So there are quite a number of equations. They use about 5 to 6 equations that you solve to be able to determine the eccentricity E and also the minimum pre-stress forces, and then the maximum eccentricity. So this is something you're going to go and have a look at. Here it's just a matter of for you to see that it's done somewhere. We learn about this thing, but I realize we don't use it too much. I think most of these softwares we use, I think this already in the back at the back end of the software, so you may not be able to see. So the inequality is for plotting the diagram and also determining the optimal eccentricity. Refer to Pre-Stressed Concrete Design by M.K. Hurst. So here there are few areas you need to take note of when you're reading. Transfer stage. In pre-stressing concrete or post-tensioning, we have 2 stages. We have stage 1, when concrete has just gained about 90%. That's when you do your tensioning. So that tensioning you are doing, that's how we call it a transfer stage. That's the stage when the load from the tendon is transferred to the section to generate that compressive resistance and the rest of it. Then when you are done with the construction and you now start putting in the finishes, asphalt, concrete, concrete barriers, lighting systems, services. Now once you have done with that, and now you allow traffic to begin using, Then now you also have to do final stressing, and now there are also stress limits that you follow. You check which is subjected to various loads now, not only the self weight during construction. This is now temperature is part of it. Traffic become part of the loading, pedestrian, and then superimpose dead load and the dead load. So that's now in service. So normally you'll see you have stress limits checked as during construction, that's at transfer stage, and then stress check at service or in service. So that is now what those are some of the things you need to think about. The cable zone, cable profile, flow chart, and detailing. All these are very, very key for you to follow when you are dealing with pre-stressed concrete girder. And here it is, the cable zone. See figure below is in a pre-stressed girder. I think it refers to the region within the girder where the pre-stressing tendons are placed. Proper positioning of these tendons is crucial for the structural performance and efficiency of the girder. Here are some of the key points you need to look at. So this is the cable zone that you need. So this is your neutral axis. So all this cable you find is actually all fall or lie below the neutral axis. Anything beyond will generate excessive stress to the members. You have the bottom and then you have the top. Here you can now play with your cables profiles to ensure that when you tension and you are checking the stresses, you don't have stress limit exceeded. It will create a lot of cracks, and cracks are not required in pre-stressed concrete. So that is something that I thought I should pick it out. And then this is now the cable profile. Cable profile is important. I've seen even on site. The engineer must be able to provide the coordinates for plotting the cables to simulate what was designed. Otherwise, if there's no compliance with design, then it will not perform the way it was designed. It will definitely have the eccentricity will be different, the stress generation will be different, and so it could be you'll be lucky if the stresses generated are within limits. If not, then the project fails. So these coordinates are very important, that they are plotted verbatim, so that what was designed or modeled is exactly implemented. The cable profile in a pre-stressed girder is crucial for ensuring the structural efficiency and performance of the girder. The profile typically follows a parabolic or draped shape to counteract the bending moments induced by external loads. So if you don't do the coordinates well, what do you expect? It will not work. You'll get into trouble. Then I think there's a flowchart. Yeah, this flowchart is normally for all the design we do. Actually, we are supposed to generate flowcharts. Then you're using the flowcharts. You are able to look at it. You give it to the junior engineer, someone fresh from campus. You can actually follow it. If there are issues, they can get back to you, and then you guide. I've seen in most literature, almost all actually, you find at least there's a flowchart that they use to guide. You can see here they talk about impulse loads, estimate the self-weight, dead loads are here, bending moment and shear force diagram, choose concrete grade and allowable stresses. All these are guided. You get them from the manuals, and then you do your iterative design and make sure all the limits are complied with. Okay, this is for uncracked member, then so you can also have for cracked members. So this I've already talked about. Magnet diagram is a graphical tool used in the design of pre-stressed concrete beams. It helps determine the optimal pre-stressing force P and eccentricity E that ensure the internal stresses within the beam remain within permissible limits at both the transfer and service stages. Transfer, this is the construction stage, and then service is now when you are done with construction and the bridge is open to traffic. So these are the geometric requirements needed to be known. Internal forces, that is estimate the internal forces, induced self-weight and moments due to dead load and live load, permissible stresses. This is something we've already discussed. Now this is now the model. Of course, this box culvert, if you look at, there was I shared a similar bridge, but that was an arch bridge, which was also 30 meters. So what I did here, just to replace the arch with the box girder. So now the next thing would be comparing materials, comparing technology, comparing the time required to construct, so that you can look at, you can now say, okay, this is cheaper, or this one is not, this is expensive, this one is something like that, in terms of material quantities, in terms of time to implement, and even the technology required. So basically that it's very important for you to say this is more expensive than the other, only when you have done some comparative analysis. So this is a 14-meter wide deck with 2 number raised walkways. It has a crash barriers for safety control, post-tension box girder, cast in situ box girder. So even the construction approach is similar to that one of an arch spandrel bridge, an arch open spandrel bridge. So this is the detail of a pier support. You have, these are the reaction block to control lateral movement in the event of earthquake tremors, or even when you have floods exceeding the headroom designed by the hydrologist. So the structure should be stable laterally. So that is where the use of reaction blocks come handy here. These are the details. This is a pier cap. Then this is the bridge bearing. We normally don't provide the design, but you have to design for it. Normally the manufacturer normally give this design. All you need to get is the reactions here, deformation, reactions, movement. That is those are some of the information you need to share with the manufacturer. Then they will give you the bearings that are suitable for this bridge type, and the bridge span and the weight. This is pier support. This is the pile cap, which I think they're all here. So this is just picking it from here and transferring it to the wording there. Okay, so let me see, what more do I have here? This is the 2D view. This is the pier support. This is 30 meters. This is where we have abutment. This is where we have abutment. Then down seems to be our normal, the 3D. This is what I was trying to demonstrate. Construction stage 1 is when you build the substructure system. Actually, I told you you can do pile system first up to pile cap. That will be your stage 1. Then stage 2 becomes substructure system, which is now the abutment stem and the pier stem. But for modeling and trying just to demonstrate, we normally we combine both the pile system and the abutment or the pier support as one. So the best, if you want to understand the stress generation right up from pile cap, you can actually do the different construction staging, so that you see the load built up in different sequencing kind of. So pier support is here. Your pier then abutments are represented with this. Then in under construction stage 2, now you have now prepared your prop system. You stabilize the foundation here to avoid deformation during construction, because wet concrete is very heavy, including construction loads. equipment and human being, and then also yeah, so you have to be careful. So this is the first stage you do. Normally for continuous member, you don't stop midway. It has to pass the support up to the point of intraflexion, where you have zero moment due to dead load. That is a good area where you can actually terminate, or else you have construction joint. You do it after that point, then the next stage is now you start from that point, and then you complete the span. So this is stage 1. Then stage 2, now you have put all the prop system in place. You have stabilized the bottom of the props to avoid any differential settlement. For most of this, I think for pile system, the settlement is limited to about, I think, 10 to 12. You need to check the Tomlinson and other foundation design book and construction textbooks should be able to give you the limits requirement. So that is construction stage 2. This is construction stage 3. Now you have 1 is the support, 2 is up to here, 3 will have finished. Okay, so that is that one. This is a demonstration. I just try to pick to demonstrate where you define your tendon properties from. So you come in here. For tendon properties, you have to you define it from here. This is where you define. There are different here. This one is where it is internal, pretension, external, post-tension, and then external. Internal post-tension and internal pretension, internal post-tension, and then external. Very interesting terminologies here. This one here. Then we also have tendon profile. This is now very interesting. This is where you have to plot. You have to plot. You see this one here. When you click on it, it's already appearing there. That's the next one. That is another one. So how do they do it? You come in here. Then you just look at the different. You see here you have the tendon name. You have the tendon property. You have the tendon group. You need to really know which group this one lies. Then you come down here. This is where you have the coordinates are very important. I told you, without knowing the coordinates and understanding the geometry of the structure, you become difficult to model. Yeah, so it's very important you get to know some of the things. Yeah. There we go. So if you want to view actually all that you have plotted, you just come in here and then you display. That's what you can view. All these have been plotted. So that is how you can actually do your stuff. Okay, so this is a demonstration of how you can put the property. This is how you do the I've already demonstrated how you do the plotting, so it should not be a problem. So all these are modeling process or procedure. Now when you have done plotting, now you need also to do the pre-stress forcing. You have to define the force. That is tendon pre-stress. So we have to come in this under this command detail. This here, this is the last part here. This is for self weight, but these are already given here. If they were not it here, you would come and go to pre-stress. You put pre-stress system here. If I click one of that, then under the load group name, you already define your pre-stress load group. You also come and put it here, and then they all come. Under this tendon, you highlight all this one here. You highlight all this, then transfer here. Then they appear. Make sure you specify the stress values given. This is the 0.7% of the no, 0.7 times the jacking force. No, not jacking force. Ultimate tensile strength, 1860. Sometimes it is 1860, sometimes it is less, 1770, depending on the cable details, and then the loading. This 1860 seems to be for long span bridges and also bridges that are subjected to high loading kind of extreme loading. But if it is for buildings, I think you can use the lower step value. So basically that is what you have here, and then you transfer your load and you're able to see everything you want to do. Then you can come down here. I've already demonstrated that if you want to view all that you plotted, you can highlight it from here and then display. If you want to hide it, you click and you do undisplay. So that is briefly what we. These are the different loads. This is I think wearing surface and services. Being a line, of course, it's designed as a line load, so you just get to know the area times the width times the load per square meter. You should be able to get that as a linear meter load. Yeah. So that is for the wearing surface. This is for crash barrier. There are two crash barrier on both sides. Each could be about 10. So having two and apply it on a line beam should be 20. And then I think down is this is raised walkways about 0.3 meter thickness and 24. That is unit weight. That's about 7.2. That is multiplied by 4, you get 28.8. Those to apply it on a line beam. So that is how this loading. Then the temperature you can do. There are code requirements for the temperature. You can apply especially for the the temperature gradient. But for the element, you just highlight. I think this box is affected by temperature. Morning is affected by temperature, so that is exactly that's what you can apply. This is now the temperature gradient, but there also here I can still also demonstrate something here. When you come to different temperature now, this is temperature element. This is also here. You can go to initial, then this is where you specify your initial temperature. Then you're about to apply even maximum, but you need to highlight it first. You need to highlight that. Then if I want maximum temperature, just highlight here. Then you put minimum is which takes you up. So this one brings you here, and then you specify. Then temperature gradient. This is where now you have to go. You go to the fly code system down here. Euro code is here. PS system. You have the temperature heating and the temperature cooling. So if you've done issue to do with the temperature effect on bridges, you should be able to get all this literature right. They are there in your notes. So you read. So these are just normal stuff. This is a loading requirement where the vehicle is on here on the bridge. Just trying to demonstrate. This seems to be LM1. These are tandem system. Okay, this is I think reaction values when you are done with construction stage. You've done your stage 1, stage 2, stage 3. That's the reaction you get. Then this is traffic load. The reaction seems to be like so. You can see that the dead load, the dead weight is higher than the live load at the pier support. You see here is 14,000 dead load, and then we have live load as that's about 15 and 5, about 30%. Yeah. So these are the different reaction values. You can experience. This is for load combination. You can see load combination now is high. It's up to 31,000, almost twice the dead load. Okay, so let me see. This is another load. Now this is the reaction dead load in service. Dead load in service. Now the other first one is you have just completed construction. It means it is this dead load due to self weight, while this one is dead load combining superimposed dead load and the dead load due to self weight. Those are the two differences. You have to mark that. And these seem to be self weight. You can see then this is you can see the difference in the response. This is pre-stress moment. It's the reverse of the number. So that is what you need to do. You need to read. This is the axial load. You can see the axial load on the deck tend to move and higher here because both sides are stressing and affecting the section over the pier support. These are the different sections that you can generate from the software. This is the PR section to give you all the properties. This is our support. This is the halfway towards the mid span, and this is the mid span. Okay. So these are the section properties that you can heavily generate using Midas. Don't need to waste much time. If you want, can do. It's already from the modeling. You can actually get it. If you model very well, that's what appears. Now there's this anchor block thing. I told you, you are going to pull. You will pull this your tension, your tendons, and then you hold it tight. It tends to shrink or to gain the original status. In so doing, is compressing because really having end block holding it properly. It tends to compress this member into compression. That's why most of this pre-stress system keep that concrete section purely in compression. Concrete is very good in compression and weak in tension. That's what happens. So for any ultimate issues and cracking and the rest of it, we have to put in some nominal reinforcements. Unlike in reinforced concrete where you put everything is done on reinforcement bars. So there are three different considerations at the end block here. As this concrete tend to be pulled inside at the anchor plate, there's deformation and cracks generation. So these cracks which are generated need to be controlled by some amount of reinforcement. So what happens is that's what we call spalling bars. You need to design for spalling rebars, reinforcement bars, which will run on the surface just after the cover to take care of that effect from tensioning or jacking force. Then the bursting. If you pull and you leave it, this thing can pop in. So remember, you have quite a lot of losses along this line, along the cable length. The pre-stress losses are many. Next time we can look at it. So it can pop in. So to avoid that, since there is high stress generation, if you can see from this figure 8.9, so along this line here, which is somewhere here, you provide some reinforcement, like they call them anti-bursting reinforcements, which is designed for. So it is actually here. Bursting stresses are tensile forces perpendicular to the axis of this concentrated load or force. These stresses are typically located away from the point of loading. Bursting rebars are provided to resist these tensile forces. So there's a professor called Guyon has already developed some formulae that people use in the industry, so you'll also have a look at. Then also within that stress block, you need to create some sense of equilibrium. So we also need what they call equilibrium bars, which are provided to maintain the equilibrium of forces within the anchoring zone. These bars help distribute the pre-stressing forces evenly across the section. The design of equilibrium bars is based on the overall force distribution and the specific requirements of the anchoring zone. So if you read about this thing, you're going to see how they design it. Mine is just to share with you what I've come across. The rest you do. This is a model. Try to just understand the stress distribution using frame. And below is a model which was done. You can actually see this is the face from extreme end. You're seeing inside, no, into the bridge direction. So you can see the stresses are going both laterally and up. So this is a section cut here, cut along here, and then you're viewing. So you can see the stresses reduces away inside in the length of the bridge. Okay, this is the deep beam analogy. So these are three. Here we have four. Here you can see three. This is the moment they are talking about. This is the stress generated. So you can actually model using solid, not plates, using solid, and then you're able to see the stress generated, and you can also use these solid stresses to calculate amount of reinforcement you need. But it's good to relate to earlier work done by the different professors. You are going to see a different formula used by different authors, which people are using in the field. So when you come across one or two, you can also try to use and compare. So this is just a model using Midas, but this is from already established literature by the different scholars. This one is from M.K. Ast. Yeah, I've already given you this one. This is from Guyon. There's a literature. I think there was a presentation, a workshop. Yeah, he attended. He made a presentation. I think there's a big book which I picked this from. If I get it, I can share that. Now, these are the different formula used. Guyon 1953 to 1972. This is the formula for bursting forces. A and D and P, they are all defined here. P is basically the plate stress, the jacking force, don't worry. This A and B are which are the dimensions of the plates. Okay, you have Leonard 1964. He has a formula here. But if you look carefully, they only have academicians only did bursting bars or a formula. We don't see for spalling and then equilibrium. But there are other existing texts that you can also read from. The BS 8110 1997 has also something here. Eurocode 2004 has it here. There are similarities actually. The Gupta, E and Leo and Dope, they all have it. Okay, then even ACI 2014, Hashito 2014, Joe et al, all these are here. Now, having done all this design, you can also have design output. How do you appreciate design output from Midas? Not to waste much of your time and confuse you. When you have done all this modeling here, you have done all this modeling, boundary, load, analysis, results. Now you come to PSC. Under PSC, you have parameters. Look at these parameters and fill them correctly. After you have done all that, you have already done your analysis, you have not the results, and you can, from the results, you are able even to see the different one, able to see the different load combinations. They're already here. You can even look at your spreadsheet stuff form. You can make load combination sheets, everything. But now you want to design to see whether you are okay or not okay. Sections are okay or not okay. That's where we go. You come in here, PAC. If you are dealing with reinforced concrete, you come to design and reinforced concrete. If you are dealing with steel composite, you come to steel composite. Steel, you have to steel. But for us, we are dealing with PAC, pre-stress concrete. So parameter is very important. And the design load. Are you designing using on a parameter? Even just make sure it is either BS, Eurocode, all these are IRSC and the rest of it. So do that. Then you come to design material. Make sure these materials comply. Grade is defined. Rebar type defined. All that. You come to serviceability. Normally, if you have put load combination by you manually, then you would come and put this thing manually. But if not, you come and there's quasi, there is frequent, there is characteristics here because we did automatic load generation, load combination generation. That's how it also picks it and brings it to. Then we do, this one is done by software exposure class. Now in the exposure class here, this is now where the knowledge of your geotechnical or material testing is very important, because you want to know whether water is contaminated, it has the chemical content is high, acidity is high, whereby you need to improve on the cover. Is it severe, very severe, or what? You need to understand that. So your code has all these conditions that you need to be able. All these are defined, the XC1, XC0. You will go to that literature and then you understand which one. So you're able to put maybe it is XD1 for the top or bottom. Then from there you come exposure class, you do shear connect and you can, if it is cast in situ, then you don't need to talk about shear connector. But if it is precast, you know, precast panels, each of the panels have the shear connectors. The way they do the concrete joints, so for them to joint, to connect well and join, and when they're joining the two and putting the bonding stuff, it works well. So you are able to specify here. Then you come here. This is now after you have done all these requirements, you do what they call perform PAC design. After you have performed, then you can view. These are the different checks, design checks. You see, check for flexure. This is check for flexure strength, check for shear strength, check for combine. This is stress for cross-sectional construction stage. Then it also check whether the stresses of tendons have not been exceeded. Then also I told you have to do at construction stage, which is transfer stage and service stage, all the way down. So I can click here, and then you can see all these are passing. So your ultimate checks, both positive and negative, for all these load combinations, the different load combinations have been checked and they're all fine. So that means the reinforcement you have put in your section is okay. For shear also you can check. Shear has some failure in some areas, so that will help you to improve on your shear rebars or section. You refine your section, revise it. So that is something you need to do all through. So if I look at the pre-stressing at construction stage, most of pass except in few areas. So all that also require you to modify. What about in service? In service seem to be passing. That would mean you need now to say at construction stage what is it that is causing this failure. You need to look at the amount of the strand or the stresses defined at the beginning, or the concrete section, or the construction loading could be more. You have to check all that. So that is exactly what. Then from there you can you can also look at the different design forces. Last time I told you the moment generated when a section is pre-stressed is different from the moment generated when the section is pre-stressed or it is reinforced concrete. Yeah, you will find it is basically different about 30 to 40%. So these are some of the things. These are the axial force. You see, this axial force is very high. That's why it can crush the member. You need to be very, very mindful of this. You have to be aware of this one. It's very dangerous. So this is you can generate this and then look at the worst case. You can use it also for designing your member if you want, but the design is already done. You have seen from here that first I need to show you something here. Section manager is where you define your reinforcement detail. You may think that where is it getting from? So the flexure and shear checks are based on this reinforcement. Do the longitudinal and shear reinforcements. These reinforcements are the ones that bring about this passing of the of the requirement, where the requirements are within. If you adjust this reinforcement and make it less, definitely something else will happen. So these are things that you have to make sure you do to be able to get what is required. So basically, ladies and gentlemen, this is briefly about box girder continuous. Next time we shall look at maybe a simple supported with a different configuration of the tendons and for just appreciation. No, this is knowledge sharing. This is not lecturing. If it is lecturing, then you have to do a bit of in-depth research and do it in a more professional way. But this is knowledge sharing. So appreciation of use of Midas. I think Midas has become dominant, and actually for us here in Uganda now, and I think in other parts of the African continent, we are using Midas a lot, and it seems to be gaining ground because of its user graphical interface and also the ease with which you can learn. Most students learn this thing very well. They have a lot of modules on YouTube that many people follow. So I think based on that is a good management tool, because you can actually be a manager and you can also carry your own spot checks without affecting performance of your subordinate. You can actually do an independent check within an hour and be able to manage a project very well. So these are the different design outputs. The red line, the red you see here basically requires you to cross-check your sections and the other details and make sure they all pass. I think for pre-stressing tendon, they're all within limits, so that means the stresses generated have not been exceeded. You saw this. This is stress for cross section at service stage. This is a moment shear and axial force of a pre-stressed member. Finally, I have some references here which I said I should share. We have one is from New South Wales, Sydney, Australia, to design of pre-stressed concrete bridges, R.I. Gilbert and this gentleman. This is a very good literature. If you read about this, if you read this thing, you're going to enjoy your bridge design. This is what I was sharing. It's a very good elaborate book from UK. I think maybe another place. Mine, I think, so they brought from UK. You have structural design documentation, concrete box girder by Scullis here and Chef. We have also design pre-stressed concrete structures by Dr. Amlan Sengupta and Professor Devdas Menon. introduction to basic concept, early attempt of pre-stressing, brief history of pre-stressing, where you compare reinforced concrete, the invention of Portland cement, and the use of steel bars between 1824 and 1940. You know what happened in 1940 when Tacoma Bridge came down. Of course, the engineering was still evolving. That one, I think, I will not even comment on, but that's what I remember when we talk about 1940 in the bridge industry. Rapid development of these pre-stressed concrete bridges happened during the Second World War. I think the war also brought a lot of innovation. To date now, we have seen numerous advancements in pre-stressing concrete technology. Type of pre-stressing, part of the thing that you're going to learn, there's pre-tensioning, and then there's post-tensioning. Under post-tensioning, you have internal tendons. Under internal tendon, you have bonded or unbonded, while external tendons, basically, this is well self-explanatory. Definitely, maybe along the way, as we engage ourselves, I will hint on, get some literature on pre-tension and post-tension. The good thing, in Uganda here, we've also done both now. When you're moving along Kampala Northern Bypass, the bridges, the overpasses that you drive through there, those are pre-tension girders. And with pre-tension, you prepare the yard, you put the mold in place, you tension the cables, and then you cast concrete when the cables have already been tensioned. So when concrete has gained adequate strength defined by the engineer, then you release. Now you release these cables. So as these cables try to regain their original status or form, they compress this concrete. So this concrete become stronger in compression because it's already been enhanced by the use of cables, pre-tension. So that is pre-tension. You tension the member before casting concrete, then you release when concrete is already in place. And they don't have ducts. While for post-tensioning, this one they do have ducts. You first cast your concrete. When you've done your concrete, during reinforcement work, we talked about cable zoning, we talked about cable profiling. So you get the cable profiles well, you insert the ducts. Then when concrete has gained its minimum strength required by for tensioning, then now you insert the cables, then you apply the tension, you apply you tension the cables on either side or one side, and then after that you using those anchor blocks or post tension and anchorage system, you are able now to hold these tension members and then release. So as it tries to regain, it compresses the girder and enhances its compressive resistance. So these ducts you can either bond these ducts, you put in grout, that is bonding, or some grease, or you leave it without, that is unbonded. So if you read, you're going to understand more the benefit and risks of bonding and unbonding. Then for external tendons, that means this just the cables are going to be seen outside. Either they run within the boxes or out, depending on how you have located them. They are not inside the webs or the slab. They are out. That's why they're called external tendons. There are also risks and benefits of using external tendons. So when you get this literature, you read more and understand. You get to know more and get to know more deeper, and then make sure you attend I think it's always good to attend a lesson in bridges. This thing of going for a workshop, you will not understand bridge design very well. It is very important. When we joined UNRWA, we had an expert from UK who was offering technical assistance to UNRWA. I think the advice he gave for management was that we should be enrolled in one of the universities to do at least a module during the end of the semester to understand it better than when you send someone for a workshop. Now, that one, someone is just trying to run through his stuff or run over certain thing. So that's how fortunately we got the money and we were enrolled to do a complete master course in bridges. All the 6 modules: the pre-stress concrete, steel composite, long span, bridge management, steel. Then also did soil structure interaction. We also did steel building, and then I think there was one, because for the bridges you have 6 modules, and then you add 2 more to make it 8. So all that we had to do it, because where would you get the authority to talk about bridges? You can't use workshop stuff. So you read this thing, but also when you get opportunity, you can enroll and then try to do. Yeah, some of you guys, you're still young and you're still students, you can read some of the things. Reading alone will cause a lot of confusion. For me, I can make mistakes here, but I go back to my notes and I correct it. For you, where will you go? It's become difficult. And then also working with accredited consultancy firm like Oriental Consultant, Global. You work with Nippon Korea, you're with Kunwa from South Korea, you have Arup consultant from UK. Some of these experts are there. We normally consult them to help us where we go wrong. I also wish you guys have such exposure so that you get a bit of proper growth in this industry. So this literature, please read, and there are more on the internet. There is RC and PSC concrete bridge, that is AS 3600, that I think was published in 2009. Understanding of pre-tension and post-tensioning of girders, page from 319 onwards. This one I was specific because it's a big book, over 600 pages, so I mentioned this one. So once you get this book, just go straight to this page, you understand well. There is a book designed to BS 5400 that was written by L.A. Clark. Please look at that one. It has very good examples and talks very well about pre-stressing system. Then Teddy S. Filio, PE, F. This will be USA, Structures Design Office. They have very, very good literature for you to read. So this is where I can end my knowledge sharing, but definitely we shall continue. Only thing is, sorry for the missing sound last time. I posted. I think maybe the discussion I made then could not maybe differ slightly from what I've made this morning, but at least thank God that this thing was corrected yesterday, and I said let me share this back with my brothers and sisters to follow this thing. Okay, this marks the end, and just say thank you so much. Let us continue to interact and share this knowledge. I wait to see your comment. Thank you for those who send in their comments saying that the sound was not there and the rest of it. Thank you and have a good day.